Hello, Cybernats. Let's just start by introducing ourselves. My name's Ben Reardon. I work on the detection team at Salesforce. I'm an engineer. Actually, I'm a structural engineer from a past life, but I've been in information security for about 18 years or so. My interests are around data visualization, and most recently I've been going down the machine learning rabbit hole and anything to do with robotics and electronics. I once made a robot guitar, which is pictured there, which is made out of an Arduino, a Pi, 6 servos and some electronics to be able to play firewall logs. It's good fun NMapping robot guitars. And also anything to do with data visualization interests me. That's some volunteer work I've done for the Koala Base Hospital in southeast Queensland to try to figure out why the koalas are in such steep decline there. So that's a summary of me.
Hello everyone, I'm Adel, lead security engineer at Salesforce, interested in anything detection, deception, and security. I'm an active member of the HoneyNet project for about 10 years now, and developer of a couple open source projects, including Honey Lambda and Honeybit. And yeah, that's me.
Okay, so in this talk, we're going to describe what HASH is, go over how it works, and show you some use cases in an attempt to try to illustrate what problems it solves. And we'll show you some of the tools that we've open sourced that you can use in your own environments to get some benefits out of HASH. So this slide is a quick tip of the hat to all of the other technologies that have played in the network fingerprinting space, most notably JAR3. Some of you might know JAR3. It was born out of the same team that we're in Salesforce, and indeed it was the inspiration for HASH. I looked at JAR3, which does fingerprinting in TLS, and said, I think I can do something similar with SSH along the same vein. So I was inspired by previous work, which is good. I mean, that's, information security space. We move the needle, we push the envelope, and we increase visibility. So this is a tip of the hat to that kind of concept. So what is HASH? Well, every encrypted protocol needs to exchange algorithms before it actually becomes encrypted. And by necessity, this is done in clear text over the wire, and it's a beautiful thing because we can have a look at those protocols and determine which compositions of them signify that you're using a particular app, because they do tend to be app specific, and you just need to figure out what that composition is in order to be able to successfully fingerprint clients and server apps. Now HASH does that with SSH basically. There's a lot of other tools around that do it with other protocols, but interestingly enough, when I first came up with the idea, I looked around and there really wasn't anything else in the SSH space. And SSH has been around since like 1995, I think, somewhere around that time. And nothing has really been done in the fingerprinting space. Fingerprint TLS and, as I mentioned before, JAR3, they do pretty much the same thing in TLS. And if you haven't checked them out, I really strongly suggest that you do. JAR3 is a fantastic product. And a quick shout out to John Aldhouse and Jeff Atkinson, who are also on our team that helped develop HASH, along with Adele and myself. John Aldhouse and Jeff Atkinson were two of the JARs, the JAs in JA3. The other one's Josh Atkins. So how does it work? Here's a bit of a timeline between the client and the server and the way that SSH works. First of all, we have the TCP three-way handshake that we know and love. That occurs just like any other handshake, SYN, SYNAC, ACK. Next up, the client and the server exchange identification strings. You can think of these as analogous to user agents in HTTP land. They're mostly ostensible. You can put in here whatever you want. The only caveat is that the protocols themselves tend to need that SSH-2.0 to indicate what version of SSH that it supports. But the rest of it after that is basically an open string that you can put in whatever you like. The RFC suggests that you put in what your product is, but you can put in whatever you like here. This is all in clear text, right? Now, after this, the server contacts the client, and it tells the client what protocols it supports for various functions in the order in which it prefers them, and this becomes really important with hash, as you'll see soon. The client then tells the server the same thing. This is part of the negotiation piece. And out of the 6 protocols there are selected 4 to compose the hash, being the key exchange protocols, the encryption protocols, message authentication, and the compression algorithms. The other 2 got left out for technical reasons. Basically, the host key changes. On the first time a client connects to a server, it's X, and on the second time that same client connects to the server, it's Y. The reason being is because the client now knows about the server, and the server's host keys are in the known host file on the client. And so now it doesn't have to have this guessing game. It actually knows what algorithms it prefers. And the language field I'll get to shortly. At that stage, they create a key for the encryption of the session itself. And then after that, it's encrypted, and things get a little bit tougher once it's encrypted. But the green portion there is where hash plays in the identification phase. In Wireshark, this is how it looks. This is an example of the client kex init packet. All of this comes in one packet, and I've highlighted in pink there the components of the hash. You can see all of the lovely algorithms there in their clear text format. I don't know what these algorithms are or how they work, but the fact is that they're all there in text, and they're all kind of turn out to be unique per client, pretty much. So let's have a look at an example of how it works. This is Cyberduck. Maybe it's a popular. I like it. It's got cyber. I'll buy it. It's a FTP, SSH, all sorts of clients. It's good for Mac. When this contacts the server, these are for this particular version, mind you, 6.7.1. It's interesting because you can actually use hash to identify different versions at times. So you can use hash to, say if you've got a vulnerable version of Cyberduck out there and you want to know if you're using it, you can use it in this way. The 4 functions that compose the hash are listed here. You can see all of the, Diffie-Hellman, there's elliptic curve stuff there, there's compression, message authentication. These are all the protocols that are supported by Cyberduck in the order in which they're supported, which becomes important because what we do is we get these protocols and we concatenate them all together in a big long text string and just put in a semicolon in between the fields so that if we want to later on we can split these out just with a regex to figure out what compression algorithms was it actually. So you can see there's lots of entropy in that string, and that's what hash leans on. And all we do now is just take an MD5 hash message digest of that, and we end up with the hash, which is pronounced exactly the same way. So that's basically what Cyberduck looks like on your network. It's got that hash value of 8A8A. Now, if we go and have a look at Ncrack, which is a brute forcing SSH tool, and these are the algorithms that it supports, you can see it's a little bit more Spartan. It doesn't support as many algorithms as Cyberduck does because Cyberduck's meant to do much more than Ncrack, which is just meant to do password cracking. Now when we concatenate all them together, a little bit less entropy, but still pretty good. We hash that, and now we have an identifier for Ncrack, which is pretty good if you can see Ncrack on your network, and normally that's a bad thing. So if you have a look at the source code of Ncrack, you can see here that it's purporting to be OpenSSH 7.1, which is fine. You can change that to whatever you like, but unless you get right under the hood and you go and change those encryption algorithms and start messing with them, the hash of Ncrack remains the same. So what you can do effectively is monitor over your network for the presence of this hash and potentially identify Ncrack in a passive manner. You're not near the endpoints, you're not near the client, you're not near the server, you're just observing the network traffic. Quick note on MD5 versus SHA-256. So we know that MD5 is subject to collisions, and we know as security people we should be looking for better. And so we looked at SHA-256 there, and we gave it a bit of a trial. But in the end, there were lots of reasons why we went back to MD5, but the main one was that SHA-256 is just too big. You can't put in a tweet, for instance, if you're trying to share an IOC with another group, or if you're trying to paste that somewhere, it's just too large. And if you're looking at dashboards, the MD5, the 32 character property, is really nice, and it lends itself to documentation. And it's also supported by everything, whereas SHA-256 probably is, but I know there's definitely products out there that don't support it. So it was the most interoperable hashing mechanism that we could use, and it provided a net benefit. We weren't really worried about collisions here. So we stuck with MD5 there. JAR3 is also MD5, by the way, so it sort of had some consistency there. The language field was interesting. We didn't know about this language field going into it. It kind of just popped up when we were looking at it. The RFC defines a language field for SSH. I've always seen it empty. I've never seen it anything other than empty. I think Didier Stevens did some looking on some old PCAPs. He looked back over 3 years of PCAPs and found nothing but empty as well. So that was left out of the hash, but we still track it because it might be interesting one day. So you can still use that as a tuple with hash. If you have seen this field, or if you go away and have implement this hash, and you see that field anything other than empty, that'd be really interesting to me. And here's some hash examples of some clients. So Cyberduck, as I've already showed you. Paramiko is the go-to SSH client and server module for Python, and that's a really important one because a lot of the exploit tools, they're developed in Python, and so it's nice to be able to fingerprint when people are using Paramiko. Paramiko is also used legitimately by developers a lot, which is a point I wanted to make. DropBear is a popular IoT library. I believe it's written by an Australian guy. I think he might actually be Canberra-based. But yeah, it's a popular one, so it's interesting to be able to fingerprint IoT traffic on your network to map out, and it's a good segue into the next talk I notice is about IoT. Rensi, I call it Rensi, that's the PowerShell SSH, one of the PowerShell SSH modules. Might be interesting to you if that's on your network, and Ruby as well. Of course, Ruby is also used by developers, but it's used by Metasploit also. Hash server examples. Once again, DropBear has a showing there. It has a server component, AWS, and an interesting one that goes to the topic of deception that we'll be covering shortly is Cowrie, the SSH honeypot, is identifiable via hash.
So before we go through some interesting use cases, I'm going to show you some implementation options we have. We actually used Bro or Zeek script as our main implementation method. We actually did the same for JAR3 as well because, Bro is one of the most common NSM or network security monitoring tools out there. It's scalable, it's passive, you can easily deploy it, you just need a tab to forward your traffic. So that's why we implemented hash in Bro script. You can just get it using a Bro package manager. So just use that for installing hash. You don't need to manually download it from our repo. And we also developed a Python script. And the reason was we actually needed a way to capture PCAPs as well, or if someone doesn't use Bro, can still use a Python script to read from PCAP file or capture the live traffic. And it also helped us debug our Bro script as well, because Bro had some bugs in the SSH module it has, and that was reversing the client and SSH. It couldn't accurately determine the direction of the connection, so that's how we debugged that and found that. Even you can also use this Python script on your servers and capture the fingerprints in JSON or CSV format and forward it to your log server. Actually, that's how I get the logs from my SSH honeypots. We also implemented a Dockerized version of this Python script just to make it easier for you guys to try and see how it works. You can build the container using the code we have in the repo, or you can pull the version from Docker Hub. And something I thought it might be interesting is Hashgem. So I thought it would be good if we can create our own fingerprint database. So one problem with JA3, I've noticed many companies and people out there had this problem with JA3. They were looking for a fingerprint database, or they wanted to create their own database, but there wasn't any automated way of doing this. So this actually is a dynamic Docker file and a simple Python script which populates that Docker file with different SSH client versions, and it builds a container, tries to initiate a SSH connection, and then captures the hash value for that specific SSH client version. So as an example, we created a sample fingerprint database, including Dropbear, OpenSSH, and Paramico. But you can create your own fingerprint database using this simple tool. And the last bit in implementation side is a NMapper script we created to scan SSH servers and find the fingerprint of those SSH servers. So as an example, you can use it to find, for example, a specific version of like vulnerable SSH servers like libSSH, which I'm going to cover in the next slide. So let's move on to some use cases. I'm sure you all heard about libSSH authentication bypass bug. This actually happened a couple of days after we released HASH, and it was interesting. So we downloaded a Census SSH dataset and generated hash for all those SSH servers on the internet, and estimated the number of vulnerable libSSH servers, which you can see it's about 2,500 at that time. So the vulnerability was the attacker could present SSH user auth success instead of user auth request and log into the servers using that. So let's see how we can detect that. If we have the hash value of the exploit tools, which are mostly based on Paramico or Ruby, so the module which was developed for Metasploit obviously was the Ruby one, and there was heaps of Python-based exploits out there which actually uses Paramico. And if we have the hash of vulnerable libSSH servers, combining these two together, we can find exploit attempts. What if we have the authentication logs as well? If we add that, we can find the successful exploit attempts, and that would be interesting.
So just a couple of other ideas about how hash can be used, potentially. If you have your production servers and you've got a relatively controlled environment, then you could potentially, what hash client that your Bastion server uses. You might use a specific version of OpenSSH, or maybe you've got an orchestration set up where you're using Ansible or something like that, which reaches out to the servers to do to do maintenance, and that's also fingerprintable via hash. So that's cool. You can say hashes from these clients are okay, but anything else, including Ncrack or maybe you can set up some logic where it's the first time I've ever seen this hash in this environment. Maybe that warrants some research, or a CCERT member to have a look at, or anything else, any other bad tools that you can think of. But that hash first seen idea is really interesting, because if you've got an OT network and it's really tied down and you definitely shouldn't see anything in there other than your orchestration server, then this is kind of like a pretty cheap and passive way of alerting this kind of activity. You can also go the other way around, and from your servers or your clients, you can say, okay, well, our supported version of SSH client is this. Here is the hash server for it, the hash value for it, and we're going to allow that. But anything else at all, including PowerShell or Paramiko, Ruby, or anything else, in fact, we're going to bump that up the alert chain, because it might be that that the client is compromised, and they've got a PowerShell obfuscated PowerShell script running, and we're not expecting to see that. So you can use it like that. This requires like a lot of understanding of your environment, obviously, and requires a big understanding of what sort of clients that are usual. So normally you have to do a lot of profiling of your environment, which Hash lets you do. You can easily dashboard your environment. Another idea that I came up with was within GCP. When you SSH using the GCP console into one of your VM instances, a lot of stuff happens in the background. The GCP infrastructure goes and puts an ephemeral client key on your SSH client key in your known hosts. Sorry, not known hosts, authorized keys file, and that allows them to connect to that server with their back-end systems and deliver the SSH session in the web browser. And this is one way of contacting your GCE instances without an actual client on your machine. You do it all in the browser. So that's good. I had a look at the network traffic by installing hash on the servers themselves, and noted that connection made by Google is very fingerprintable. And I'll just make a note. Hope you can see that it's a bit small, but those four black lines there indicate the protocols that GCP are using. You can see that it's very, very Spartan. Now, this time we've only got one single protocol for each one of those functions. So because Google can do that, I guess, because they know exactly what is supported on that box. They don't have to have this big line of, oh, these are all the things I support, and hopefully we can agree on one. They can be very efficient there and just list one per function. So maybe you can say anything else. If anything else contacts my GCE instances, then I want that bumped up the alert chain.
So now my favorite part, my favorite use case of this hash is to detect lateral movement activities. As we know, attackers usually use system's default SSH client for lateral movement, but not always. There are cases like Empire's invoke SSH command, which that PowerShell script actually uses renc SSH.NET library, and obviously that has a specific client ID and hash. And as you can see here in a screenshot of the Empire code, you can see they've mentioned that they're using a base 64 encoded SSH.NET .dll. So we can actually detect such activities easily. But what about Cobalt Strike? Guess what? Cobalt Strike actually has a built-in SSH client and I've noticed that a couple of weeks ago, and had a look at the documentation. So they actually added a SSH client in 2016, which is actually baked in. There's no way you can change that. And the thing is, Cobalt Strike is a Windows tool, and this is one of the only Linux-based modules that it has. It would be interesting if we can detect such activities. So if I actually generated the traffic and had a look at the hash value and noticed that there is a specific string, like as you can see here, it uses libSSH2, a specific version of that with a specific hash value. If you search that in your network, you probably find some false positives as well. But if you limit your search to Windows source, to Linux destinations, and just look for internal SSH connections, so we don't care about outbound SSH, just limit your search to internal SSH connections and just from Windows to Linux systems. That generates like no false positive. And you can easily detect the attackers laterally move through your network using this Cobalt Strike module. I thought it might be interesting to both blue teamers and red teamers, as Cobalt Strike is one of the most favorite red teamers tool. Another use case, which isn't like really defensive, is to detect SSH honeypots. As you can here see in the screenshot, which is a part of Cowrie honeypots code. As you know, Cowrie is one of the most popular SSH honeypots out there, which is based on Kipo honeypot. And unfortunately, they use a static list of ciphers and algorithms which can easily be fingerprinted. So you can see here we have two hash values for it. For some reasons, which I'm not going to discuss here, it generates two hash values, but that's really unique. I actually searched that in Census database and Shodan and found lots of honeypots. So as the defender side, we actually need to improve our honeypot codes. I actually sent a pull request and fixed that. But there's also another one, libSSH module in Symmetria honeypot. Also is very fingerprintable, you can see here. And yeah, that's one of the other use cases we have.
Just staying on the topic of evasion. So I've got a number of, as part of this research, I set up a few sensors on the internet and just tried to figure out what the internet noise looked like in, with regard to hash. And here's just a bit of a table showing you a couple of botnets that I saw, some of the cred stuffers or brute forces out there. So Go has its own hash value. We can fingerprint that, and it's that 72, the one in the red box there. Some botnets don't bother masking their client identification string, which is basically like, as I said earlier, the analogous to the user agent. They just don't bother. They just said, yep, I'm Go, it's all good. But some of them with the same hash, so we know it's Go, they do deceive and they purport to be OpenSSH. So they're saying that there's something that they're not. That's interesting in and of itself. But interestingly for this botnet, you can see that the client identification string changes for each IP address. They postpend, a string, and it's always got an underscore and then 5 characters, and they're always unique. I had a bit of a look at this. I don't know what. It's probably just random, these strings. Initially, I thought maybe it's some, it kind of looks like if you put them all together, it might be base 64. I'm not sure, but I was never able to find out what it meant. It's probably just random if you apply Occam's razor there. But that took me half a day of research. Now, there's a lot of these things too. So this botnet's pretty big. and this is just a set of them, and they're all different. And then I just did some geomapping, and that's where a lot of the geomaps look like actually for a lot of scanners. Another botnet that I thought was interesting on the topic of you know, the bots like being deceptive. All of these 4 graphs have the same X timeline. You can see that the green graph there is just the IP address. I've just masked the IP address, but all of these scans on my sensors were from the one IP address. So that's good. We've got the same system. And they've all got the same hash value. So we know that it's the same, you know, it's the same client software that's actually doing the scan. And this is where it gets interesting. This is the graph of that client identification string. And you can see that the strings are actually all being cycled through. So they've got some script in the background that's using the same client software, but purporting to be different clients at different periods of the scan. So it's, at one stage, it's saying it starts off saying it's putty, and then it changes and it goes to OpenSSH 5.3. It says it's, what's that? OpenSSH 6.2, and the Aqua one is a product called Netserang Computer. It's an SSH client that's used. So it's using 4 different client identification strings. Now why do they? And all of the accounts that were being scanned, I just joined these with the auth logs on my sensors to get a sense of what are they looking for. And this particular botnet was all looking for root. So why are they lying with that client identification string? Well, I think that the reason is because there's tools out there, and I think Suricata has a, you can basically like shun network connections based on a match of client identification string. So if you think fail to ban or SSH guard, but with client identification strings, you can actually shun connections. And maybe they were looking to get around such controls. If anyone is looking for that sort of stuff, then this particular technique would get around those auto shun kind of systems. And that's the only reason why I thought that this would occur. Where do we go to? So industry support. We released this, I think it was in November, October or November, I can't recall. But since then, a lot of places have picked it up and given us support. Grey Noise was one of the early ones. They're a fantastic organisation. Binary Edge, Cowrie actually. If you download the Cowrie SSH, they will actually document the hash value for you as well, which is actually quite ironic because we can fingerprint Cowrie. Oh, sorry. 5 times. Okay. And yes, lots of other great support there from some organisations. There's a QR code to the open source repository that we put out last year, if you want to have a greater look. And if you've got any questions, I believe our time's up, but definitely hit Adel or I up after the talk. We're interested to hear about anyone who wants to do some research in this area to go along on that ride with you. So thanks very much. Thanks Kylie and Silvio for organising the conference, and see you next time.